it's 1/2. What is the power of L? On the left, there are no L's, so it's just 0 power. Okay? Zero equals alpha plus beta. So what is beta? Is 1/2. What is gamma? Okay? So what do I find from this? Let me also find the result. I find that the time for free fall will depend on will be proportional to this sign means proportional to, okay, this thing here. It's proportional to H over G to the 1/2. So the formula that I'm looking for must be something like T equals some constant where this constant is just a number. It has no meters, seconds, etc. It has no dimensions because I took care of all the dimensions. So the formula must be T equals some number times the square root of H over G. Now notice what I found. I found basically how the formula depends. How can it depend on the quantities H and G? And I also found that the acceleration, the time it takes to fall down so many meters, H, does not depend on the mass of the object involved. This is an important conclusion. I think it was you who asked, maybe it depends on mass. It's a very valid question. It's a very important conclusion. It is one of the most important results that Galileo first showed, that the time it takes to fall down is independent of the mass of the object. Now you may ask, well, if it is so simple to show that this formula does not depend on mass, why did it take people so many ages? And Galileo did so many experiments. And you may also ask, well, where is the experiment? You are telling us that in science we learn everything from experiment, and here I do a little trick with some formula and get the right answer, and I discovered, it seems, I've just discovered that the result does not depend on mass. How come? Why is it so easy? The reason it's so easy is because in dimensional analysis I have assumed that the formula, the correct result, depends only on powers. Before doing the experiment, Galileo was trying to see if it depends on mass or not. He showed that it doesn't depend on mass by doing the experiments. And by doing the experiments, he also showed that it depends on H and G according to powers. he found that the correct formula for the distance, the height to fall down in t seconds is proportional to g times t squared. The distance gone in free fall increases as the square of time. This information is found by experiment. The key point is, before doing the experiments, Galileo didn't know the answer, but he even did not know that the answer would be some power of t and g. I have assumed one result in doing dimensional analysis. Dimensional analysis always assumes that the result, the formula, is a power law. But before doing the experiments, we didn't even know that. So the reason this works, and it seems like a magic, in one line you can show, as if without doing any experiments, it doesn't depend on mass. That's because I already assumed that I am going to look for a power law. But before doing the experiments, I don't even know that the result is a power law. It could be some more complicated function. So if you want to show that the time it takes to fall down does not depend on the mass of the objects, you really have to do the experiment with different masses, because you don't know that it's a power law, what the formula is. But once you have some guess, some idea, which essentially comes from some experiments, that the result is a power law, then you can figure out what power of each quantity is involved. Is this clear? Now it turns out, as you will see as we go on in the course, that most formulas that we will use, most of the important laws, are indeed power laws. Okay? Therefore, this dimensional analysis is extremely useful. Why is it useful? When you are doing a complicated calculation, you may make mistakes. Okay? And at the end of the calculation, if you want to check, you have derived some result. Okay? If you want to check if it's right, you just put in the dimensions of everything. And I do it all the time in my research. I make a calculation. I can give you an example. I calculate what is the acceleration for a star, rotating star, spinning very fast, to slow down. And I guess that this depends on the magnetic strength of the star. It may depend on the radius of the star. Okay. It will depend on if there is any mass from another star falling out of the sky. All of these things will have to break it. So I write down a complicated formula, and then I try to calculate something else, and I write down some more complicated formulas. And at the end, I have some formula with, something to the power 13 over 11 times something else, the magnetic field to the power 7 over 15, etc., etc. Very complicated formula. I'm going to use this now. Now, first thing I do is I check it. I just put the dimensions of everything and see if the right-hand side fits the left-hand side. Or you may just not know the formula completely, some piece is missing, but you have a good guess that it is a power law. Then to see what power it is, just like we did here, you use dimensional analysis. It's also useful for a student, as I said, if at the end of, you are solving a problem for homework or in the exam, and you end up with a very complicated formula. Okay, and you suspect that I have done something wrong. You don't have time to go back to the beginning and check. Just check the dimensions. Okay? So that's what dimensional analysis is about. Any questions about this? Now, let me give one other example of dimensional analysis. In nature, there are some very important numbers. And we have seen some of those already. What do you think may be an important number? Basic, what we call a fundamental constant of nature. The constants whose numerical values we give in the book at the beginning. What are going to be important constants? Gravitational constant, yes. Of course, that's an important constant. By gravitational constant, the really important one is not this little g, the how an object that I drop will accelerate. That's important also, but that's only about the Earth, how things fall to the Earth. But the more important gravity constant is a constant that tells you how any two masses, a star and a planet, or two stars, attract each other. We will learn about this later on, but I'm just using it as an example. Okay? I will give you the result, give you a formula.